Yeah, Otmar is a colleague, a dear colleague in Munich, and he's leading there a research group at the Lung Center of the Helmholtz organization. That's, by the way, the same where I'm working as well, but in a different institute. And I think Otmar is a very known person in the field of pulmonary delivery in aerosol medicines, also active in ISAM, the International Society of Aerosol Medicines. And I think that is all what I want to say about him in order to leave him as much as possible of the time and the floor. Otmar, I look forward very much to interact you again, although still virtually, but I look forward to your presentations as we all do. Also, you have to unmute.
Okay, sorry, guys. Okay.
Yeah, now it's fine.
Yeah, sorry. Thank you, Klaus Michael, for this very nice introduction. And I'm honored to was invited to open this very exciting meeting today on exposure models for inhalation and associated devices. So just to give you a flavor of what I'm going to do, I'll talk a little bit about lung deposition, just as a background, maybe for the entire day also. And then I will go into in vitro models of the lung, and I will highlight the important role of cell-delivered dose for translational purposes. And then, of course, the main topic is the aerosol exposure method and specific technologies. And then I will close with a pro-con discussion and some applications.
Otmar?
Yes.
Can we see the slide, please, Otmar?
Sorry?
We don't see your slide.
Oh, come on.
We cannot see your screen yet.
Yeah, you have not shared yet.
Oh, you did. Share.
Yeah, it's coming.
Host has spotlight your video, everyone unmute myself.
And now I think if you could move to the presentation mode, it would be even nicer.
It's weird. I thought we had this all lined up. You guys are in my way.
We see your screen well. You just have to put the presenter mode on.
Yeah. But all the stuff from the Zoom is in my way, so I cannot click the button.
It's bottom on the bottom.
Yeah.
Screen. Okay.
So
here, exactly.
Okay. Yeah, I'm sorry.
Very good.
So yeah, a little bit background on aerosols. Of course, they come in all forms and shapes, from ambient, from combustion, tobacco smoking, cigarettes, e-cigarettes, pesticides, occupational aerosols, and pharmaceutical aerosols. And they range in size, basically from nanometer to hundreds of micrometer. But for inhalation purposes, we are typically only focusing on smaller than 10 micrometers because that is the maximum we can typically inhale. So looking at the lung a little more detail, when you go through the trachea into the lung, you first encounter the bronchial epithelium, the bronchial part, which is covered with a relatively thick mucus layer of about 8 micrometers. Then as you go deeper into the lung, you come to the small airways and the bronchioli, which still have some mucus, but much thinner in thickness. And then in the alveolar space, where the gas exchange takes place, we only have a very, very thin liquid lining fluid, which is less than, well, 100 nanometers in thickness. The alveoli itself are only 250 micrometer in diameter. And here you see like a honeycomb structure, which is where the gas exchange takes place with the bloodstream. Aerosols, as they come in, deposit in different regions of the lung due to different mechanisms. And the upper airway tract, it's mainly impaction. So the aerosol, when it has to divert the direction in the bifurcation, if it's big enough and heavy enough, it will not be able to make the turn, and it will impact due to inertial effects on the walls. Then further down in the bronchial part and also in the alveolar part, there is gravitational sedimentation as a main deposition mechanism. And for the smaller particles, typically smaller than 200-300 nanometers, diffusion, molecular random motion of the gas hitting the aerosols, leading to diffusion of these particles, will result to deposition on the walls. And if we have very large fiber-like particles, they can also intercept, because as they rotate when they go into the system, due to their extreme length in one dimension, they may hit and touch the wall and therefore deposit preferentially. So in the lung deposition, I mentioned it is following different mechanisms. So in the upper airway, just a very large particles impact on due to impaction. As you go deeper, it's still the very large micron-sized particles which deposit even in the bronchioli, although here we get a few of the smaller particles also to deposit. And in the alveolar part, you have two modes, many people forget about that. They mention the nanoparticles. Yes, of course, the nanoparticles deposit efficiently of the order of 30–40%. But the microparticles, where all the pharmaceutical aerosol is, also deposits very favorable. So we have both modes, micron and nanoparticles. Here is a cartoon. We also work with animals, with mice, and we do aerosol deposition to the mice. And here you see an image of co-mapping of the lung in green, and red is the aerosol we deposited. This is a 3-micron aerosol via inhalation. And I will activate this 3D movie here. So you see here, this is just the tissue itself with the bronchial tree. It goes deeper in the bronchi. You still see the bronchi here noted. And this haze is basically the alveolar space. And then we can overlap the aerosol. This is the red part. And when you co-map it, then you will see how uniformly and nicely spaced throughout the entire lung this aerosol is deposited. And this is, of course, the reason why we're interested in this, because aerosol deposition is taking place and really spreads throughout the entire lung. And funny enough, although this is, as we just said, it's omnipresent aerosols, there's almost a complete lack of aerosol applications in preclinical studies. And the reason for that, in my opinion, is mainly the lack of easy-to-use, efficient, reliable aerosol devices. But I think the technology is catching up now, and we are getting in the position where hopefully this limitation is overcome relatively soon. So cell-delivered and tissue-delivered dose and in vitro models. Yeah, the in vitro models, I will not talk about much because the rest of the session, the whole conference will be on that, but I just thought I'd give you a little bit of an outline of the models available. So I typically discriminate between top-down approach, which is basically the animal approach, where you take the full animal or isolated perfused lung, or just a lung slice, or even lung cells from animals or humans, for that matter. And then for the in vitro side, we do a bottom-up approach typically. So we started early on with single cells, maybe multi-cell cultures under submerged culture conditions, or later now on air-liquid interface exposures where we have gas contact and aerosol contact with the epithelium. Then, of course, we have reconstructed barrier models, like the pseudostratified 3D bronchial epithelium, with or without fibroblasts connected. They can be from patients or from healthy donors. Now, even more recently, we have these on-a-chip models, lung-on-a-chip models, where now also medium perfusion is introduced and cyclic cell stretch is introduced. So the breathing and blood circulation is coming into the picture. And ultimately, this can be connected to define something like a reconstructed organism. So as I said, I think all of these these are all presented in the talks following. And also my postdoc, Ali Doriab, is presenting a milli-lung concept, not a micro or lung on a chip, but milli-lung concept, and introduces a new membrane for cyclic stretch because the typically used PNMS membranes have their disadvantages. So, of course, with all these models, you have to pick the right model for the right question. That in itself is probably worth a talk, but it's not my topic today. So I will talk about the aerosol delivery systems. And before I go there, I want to highlight a very important issue, which is the cell-delivered dose issue. So if we do in vivo modeling or human exposures, and we want to see the outcome, the health effects or therapeutic effect for that matter, then you expose your model. So you have a concentration of aerosol, you deliver it to the subject, and then it deposits on the tissue. And there's many factors, yeah, from exposure, yeah, just the concentration of aerosol in air, to the delivered dose. Many factors, I cannot go into that. But the crucial issue is that the toxicological or the therapeutic effect is related to the delivered dose and not to the exposure level. So once we have that delivered dose, we can define something like low observed adverse effect level or efficacy levels. And then we have to scale over to humans. That typically requires a model human susceptibility factor or a safety factor also. So whatever you find in your model, you have to scale up typically in those to go to humans for the safety issue, and then you go backwards, and then you can define a safe exposure limit or an equivalent dose for efficacy for therapeutic applications. But the important issue is exposure is not what we need to translate. Yeah, if you do exposure level comparison, it has nothing to do, because what the biology sees is the tissue delivered dose. So just saying, oh, the exposure level like 5 milligram per cubic meter in animals is not toxic, so it will also not be toxic for humans. This is not going to work. We have to go through the tissue delivered dose. Aerosol exposure. So here is the air-liquid interface system. What do we need to look for? As I just said, dosimetry is really important, the cellular dosimetry. So we want a high deposition efficiency and possibly even a real-time dosimetry tool to support that information. We want high dose rate. Why? Because that reduces the amount of time to have to sit there to get the dose you want delivered to your model. And ultimately, this dose rate is a function of the deposition efficiency of the concentration. Yeah, here's the exposure of aerosols and the air transport rate. So it's a relatively complicated function and not always easy to handle all these parameters. In addition, you want no adverse effects, of course, during exposure itself, so no particles in the air, no reaction of the aerosol gas with the culture medium, could be artifacts introduced by that. You want a uniform spatial deposition on the cells, and hopefully this system is easy to use because aerosol systems can be quite complicated. So what are the types of technologies we have available? There is the parallel flow device where the air is just flowing by the transwell insert. Then there is the stagnation point flow system where the aerosol is transported towards the cells, which are down here. And then this flow is radially traverted outwards and then goes out here. So basically over the cells, there's a radially outward flow, which has advantages I will go to in a second. And the last setting is the cloud settling, where you generate a very, very dense cloud of aerosol just above the cells, and you let the particles deposit. So what are the deposition mechanisms? Diffusion and sedimentation, just as in the lung. Yeah, this is for those cases true. And then since this is typically not very effective, you enhance it sometimes with electrophoretic forces. So you apply an electric field, you charge your aerosol, and then you get enhanced deposition. Or even without charging, you put the aerosol between two different temperature plates, a hot plate and a cold plate. And the hot plate, due to the higher kinetic energy of the gas molecules, temperature is directly related to kinetic energy of gas molecules, you get more energy transfer from the hot particles, then from the cold particles, and that drives the aerosol from the hot to the cold plate. That's called thermophoresis. For the cloud settling, I will describe what that is. So single particle settling is basically well known. Gravimetric force pulls it down, the drag force in air holds it back, and then there will be a steady state settling velocity for 5 micron droplets. That's only about 0.0101 centimeters per second. So it's a very meditative process. It takes a long time, even for a few centimeters to go there. For the cloud, if you have a very dense cloud, what happens is there's still the same 5 micron, but when the cloud settles, the air wants to go around the cloud, not through the cloud. So then the drag force is only applied to the outer part of the cloud, but the gravimetric force, which is related to the mass, is applied to the entire ensemble of droplet. And that can result to massively accelerated settling speeds. And that's what's taken advantage of with this cloud settling technology, which I will go into a little later. Stagnation point flow system. Here is an illustration of the flow profile. This is by far the most commonly used system in the past. And the stagnation point flow means there's no flow at this point at the center. So here are the cells, the flow is coming in, aerosol air is flowing this way, but here there's actually a stagnation point flow, no airflow. As I said, its spatial uniformity is really high in terms of aerosol deposition, but the deposition efficiency, which is plotted here in percent versus some kind of a scaling number, is relatively low. And if I say low, I mean, okay, if you have 50 nanometer aerosol to 500 nanometer aerosol, typically you have about 1% or so deposition efficiency. Of course, if you go to larger particles or to smaller particles, diffusion on the smaller side and sedimentation on the larger side will enhance that. But typically, it's really hard to get much above 7 or even 10%. Yeah, that's just a little introduction and background. Then what components do we need for these aerosol cell exposure systems? You need an aerosol generator that should be stable, clean, pathogen-free. We should measure aerosol concentration. Then we should humidify the air, because for the cells, of course, that is vital. Then we should have the deposition system. And finally, of course, we should look for the cell-delivered dose with various techniques. And there's analytical methods, typically. You can determine some kind of ion involved in your aerosol, or we can use the quartz crystal microbalance. I will explain that in more detail a little later. For the cloud system, of course, we have a generator, but we do not measure aerosol concentration. There is no need for humidity control because we put so much liquid via the aerosols in the air so that we don't need that. So it's technically somewhat simpler than the other systems. So quartz crystal microbalance, what is it? It is a real nano tool. Yeah? So here's the quartz crystal and it's put into vibration. Here's a depiction of it, how it's in the transwell insert system. And when you put this into vibration, so it's vibrating at 5 megahertz. And if you deposit onto this quartz some mass, this vibration frequency is going down. Yeah, that's a resonance effect which you have with a tuning fork. A bigger tuning fork sounds lower, has a lower eigenfrequency than a smaller one. And that's exactly what we use here. And this change in eigenfrequency is directly related to a change in mass per area. And so you can directly measure from this change here the mass per area on your cells. And this is a first principle method. You do not need to calibrate this. Just comes out of the properties of the quartz itself. So no calibration needed. Of course, it's good for quality control, obviously. It has a low detection limit. It can measure a single atomic monolayer of substance. Yeah, that corresponds to about 18 nanogram per square centimeters. and it's real time. You see immediately what's going on in terms of the symmetry. You need to make sure that the aerosol is deposited uniformly, otherwise you get artifacts. And the aerosol needs to be dry. It cannot be wet for reasons. Because if you have this vibrational motion here, there's decoupling. A liquid, it decouples from the crystal, and therefore it cannot measure accurately the dose. So specific aerosol systems, and I will browse through this relatively quickly with many and focus on a few. So the radial flow or stagnation point flow system, electrophoresis enhanced, we have one from Vitrocell systems. Here's the exposure module, which can be integrated in a bigger system, and it can even be integrated into an automated system, where many things are automatically controlled, temperature control, flow control, and so forth. It's highly adaptable in terms of inserts, and electrostatically enhanced, 10 to 15% deposition efficiency, and it has both concentration, aerosol concentration, and dosimetry measurement with the QCM. Then we have from ETIM, the Fraunhofer Institute ETIM, we have the PRIT system, which is also stagnation point flow, but it's thermophoresis enhanced, and it reaches about 35% of deposition. Another available system is the so-called NaziVid. You can buy it from the inventors. I put the link here. And the unique thing is it has a bipolar charged aerosol, and it uses electrophoresis enhancement with this bipolar charge setting. And they reach about 35% deposition efficiency, relatively independent of aerosol size. Then we have the EVE system. They use unipolar charging and unipolar electrophoresis. Aerosol comes in here, and this is a parallel flow, not stagnation point, parallel flow. So the aerosol flows here, and the cells are sitting down there, and they reach about 30 to 50, 65% deposition efficiency. Now, this is a system I want to spend a little more time on. This is the Precise Inhale technology, which is basically this aerosol generator. And it can be connected to metered dose inhalers or dry powder inhalers or medical nebulizers or just powder, any powder. It can be like soot, for example. And then it can also be on the downstream side. So it's generator, it can measure the aerosol concentration coming out of it. It can be exposed to an air-liquid interface cell exposure system, which I will talk about in just a second. And it can also measure the dissolution of aerosol on the lung lining fluid with this dissolve it system.
Otmar, 5 more minutes.
Oh, 5 more minutes. Oh, wow. Oh, God. Amazing. Okay, then.
Do your best. Do your best.
Actually, 5 more minutes, that's not possible. Oh, well, yeah, you're probably right. Okay. Well, let me focus then. And so it's a high pressure. You put the powder in here. There's a high pressure air pulse injected, which brings the aerosol in the chamber. And then from this chamber, there's a continuous flow of air in the exposure unit. And as I said, this is for the powder system. This is really easy to use and very controlled, uniform deposition. You can see it here. I'll speak over that. Then I want to briefly go on to the cloud settling issue and the cloud settling device from Vitrocell. And I have to disclose that we have patented this. So we've licensed this to Vitrocell systems. And we use a medical nebulizer for that. Cells are sitting on the bottom. It's equipped with a quartz crystal microbalance. So this is a vibrating mesh nebulizer with a high output rate. And this liquid, so we can only work with liquids here, not with dry powders, cloud is injected in the cloud exposure chamber. And then in the next step, there's a vortex formed down here at the bottom, which mixes the cloud into a uniform mist. And then the cloud settles very quickly within minutes onto the system. So I'll skip over the movie here. We have very uniform deposition. in the system, and the QCM really is very predictive, and I have to skip over this now, very predictive for the dose delivered. And now they have these relatively compact and touchscreen devices. The deposition efficiency, so the liquid you need is depending on the type of cloud you're using, it's 100 to 200 microliters, or you can go lower with this new Cloud Max system, which is just a cylinder directly over the transfer inserts. There you can use 10 to 30 microliters. Deposition efficiencies are of the order of 20 to 40%. But the main issue with these systems is actually the dose rate. Deposition efficiency is important, but dose rate is also very important. So here I have the dose rate in some units in the human lung. And just look at the number 10 to the minus 3, 10 to the minus 4. For these stagnation point flow systems, you get about 10 to the minus 4 and higher, 10 to the minus 1. So they are of the order of what you see in the lung in terms of deposition efficiency per area, of course, and they go higher to about 100-fold higher. But then it's still typically you need to wait a long time until you get the doses needed to induce a biological response. So that's why it's really helpful to have this electrophoretic and thermophoretic enhancement. It gives you about 10-fold higher. And with the cloud settling, you get 1,000 to 10-fold higher fluxes. So that's why we operate within minutes, and other systems typically operate in a time scale of hours for exposures. So examples, so there were lots of toxicity measurements. This is for soot and TRL2, toll-like receptor 2 gene expression analysis. And with this specific study, the study is down here, they show that for primary bronchial epithelial cells with macrophages, you see more response, they do this in both, than without the macrophages. But the trouble here, of course, is this is a very, very small response at about the highest dose they can manage to get there. And so for these high dose events, it's the cloud system is more apt because it's easier to get the doses there. And we have now done this toxicity study with soot and zinc oxide nanoparticles. And you see that the IC50 value, it's hard to see maybe, but it's the order of 1 square centimeter per square centimeter for zinc oxide, and so the order of 15 square centimeter for soot. That means there's a 20-fold or 15-fold difference between the two. And if you go to in vivo data, you see that this shift in hazard factor is also 12-fold. So you see that the relative change is actually quite well predicted by the in vitro system. But the total dose is remarkably different. So in vitro for the soot, we get typically 5 to 50 square centimeter per square centimeter to get IC50. In vivo, you're order of 100 to 1,000-fold less in terms of stoichiometry. That we have observed times and again. We're not sure why, but that's just the way it is. And I think we have to cope with it one way or the other. Then this can also be done for drugs, of course, those response. I think I will not go into this now. I want to close with the pharmacokinetics issue, where you have inhaled aerosol deposited on the lung and then transported into the blood. And we mimic this here very nicely with aerosols on the air-liquid interface cell culture deposited. And then, of course, some of that aerosol or drug is transported through the barrier into the medium. And that is then our representative of the blood. And of course, this transport mimics very nicely the situation in the lung. We have done this for liposomal cyclosporine, an immunosuppressant drug. And you see the transport here as a function of time. It's very steep initially, and then it flattens out after maybe an hour or a few hours. And this is a so-called burst-like deposition or of kinetic profile, where you have initial steep and then a slow rate of transport change. For submerged conditions, which is the current standard, you get this kind of profile. You get a very slow linear response, which then flattens out. And that has to do with the fact that under submerged conditions, the drug is not directly at the cells. It takes time to get to the cells. And that's why you have this relatively flat initial transport rate. Yeah, and we have done that, as I said, for the liposomal cyclosporine. Then you have to, this gives us the transport from the blood, from the lung into the blood. But of course, there's also clearance from the blood via liver and other mechanisms. So yeah, as I said, this is done with the in vitro system. And when you combine these informations, then you can predict very nicely the clinical outcome. The dots are actually the measured clinical outcome. It is a blood concentration of LCSA versus the model, and the model includes the in vitro parameter. There are limitations. One of the limitations I need to mention, aerosolization may destroy your active agent, or at least reduce the bioactivity. So we've done that for TNF-alpha, for example. For non-aerosolized, you get a higher IL-8 induction in cells as for aerosolized, and we attribute that to just degradation of the TNF-alpha due to the aerosolization process. So in summary, aerosolized drug delivery is an important part of more physiological in vitro models of the lung. Aerosol exposure technologies are becoming available. They're now reasonably simple to use, and there's also methods for real-time dosimetry. And I want to highlight again, the cell-delivered dose is really essential for in vitro and vivo human translation. And with this, I'm happy to take any questions you might have.
Yeah, thanks a lot, Otmar. Very nice presentation. I again learned a lot and things became more clear. You made the basics very clear, which are important. I have to ask now the organizers how we do this. We are actually already a little bit over time. Should we nevertheless give a few minutes for questions, or should we postpone that to some later stage?
No, I think. Thank you, Klaus Michael. So I think we can take at least two questions. There were several questions raised from the audience, and once again, Otmar, very clear presentations. So if you don't mind, there are two questions which could be answered by you. The first one is, could the large difference in dose that you see an effect in vitro versus in vivo be because the outcome you measure is very different?
Yeah, of course, everything is different. Yeah, the model is different, it's very limited, of course, in complexity typically. The endpoint is different, as you point out. And also, I think what we're overlooking is the uniformity of deposition is not really uniform in the lung. Yeah, there's hotspots in the lung, and maybe those hotspots are actually driving the biological response. That's just an hypothesis. This has not been proven. Yeah, but these are possible reasons for why we have this difference. But to be honest, I was very surprised. I always thought the biological organism should respond less aggressive, yeah, because there's dampening mechanisms. But it seems like the cells are really responding relatively soft and not very aggressive. So anyway, it is a large difference, and I would appreciate your input on what the reasons are. I gave you some of my thoughts.
Okay, last questions. Also, there were many, so that could be, let's be responded offline. So the question is, if we control the aerosol flow rate, concentration, and similar dose deposition, could we still compare results obtained with different inhalation exposure chamber systems that you described?
Yes, in principle, yes. But there's one more additional factor which I did not mention. So the biological response also depends on the dose rate. So in other words, it's a difference if I give the dose in a few seconds or if I give it over a year. Yeah, clearly that must be a difference. So if you give it in a short time, you get a higher dose as you would if you would stretch it over a longer time. So if we also account for the difference in dose rate effect, then this could explain it. By the way, this could also be some of the reasons why in human exposures the dose rate is typically lower than it is in vitro systems.
There were many other questions that should be, let's say, answered offline for a sake of time. Thank you very much, Otmar.
You're welcome.
Otmar, you can reply to those questions directly in the Q&A by yourself, your panelists, so you can take the time during the conference to reply to each of them.
We'll do so.
Good.
Okay.